Imagine a payload in motion, a critical webhook fired from your server. If your system crashes mid-flight, that payload is lost, leaving the receiver waiting. To build a reliable webhook delivery service, we have to engineer strict guarantees. We need precision around database states, concurrent task handling, and automated retry mechanisms. Relying solely on mocked unit tests is insufficient. Mocks assume perfect infrastructure, but production networks and databases are often unpredictable, highly concurrent environments. This diagram illustrates our solution, a three-tiered testing perimeter. We start at the core with pure Go logic, expand to real infrastructure, and finally validate the entire system end-to-end. We are applying this perimeter to Webhook Relay, the delivery service we're building in Go. Our progression moves outward. We will validate atomic mathematical functions first, then test concurrent database locking, and finally push up against operating system constraints like graceful shutdowns. Expanding our testing boundaries from the innermost execution logic outward allows us to systematically verify distributed system behavior long before we deploy to production. At the innermost layer, we enforce strict isolation. There are no databases, no HTTP requests, and no external dependencies allowed in these unit tests. This flowchart maps our isolated execution nodes. We first target state machine transitions, verifying a webhook moves from pending to processing or failure. Next, we validate exponential backoff calculations. Finally, we test HMAC signature generation to confirm payload integrity works. By keeping this layer confined to pure Go code, these tests execute in microseconds. Achieving deterministic, fast validation of these raw business rules is a mandatory baseline. We have to confirm the math works before we introduce external I/O. Moving to the next layer, we encounter non-deterministic I/O. Mocking the database here carries the risk of hiding critical transactional bugs and concurrency race conditions. Instead of mocks, we spin up real Postgres infrastructure inside a Docker container using test containers Go. We run actual database migrations and execute our repository methods directly against real SQL tables to verify schema constraints and transaction behavior. This setup lets us test a specific concurrency problem. What happens when multiple worker Go routines attempt to pull the same webhook event from the database queue simultaneously? This illustrates our locking mechanism, for update skip locked. When one worker strikes a row and claims it, subsequent workers immediately bypass the locked row, targeting the next available event. Firing concurrent Go routines physically confirms this claiming logic prevents double delivery. Using real infrastructure during integration testing is the most reliable way to catch these non-deterministic locking issues in a concurrent Go application. Now we expand to the outermost perimeter, testing full system cohesion across the network boundary. For our end-to-end testing, we start the full API server connected to the real test database we just configured. This outlines the full pipeline. We send a simulated webhook via HTTP, track it through the database, and spin up a mock receiver. With the lifecycle running, we test network failure resilience by configuring the receiver to return a 500 error for 2 attempts. Through the API, we verify that the service registers the failures, updates the delivery status, and triggers the backoff loop before finally succeeding on the third try. Running these full lifecycle tests verifies that internal database states synchronize correctly with external network events. We apply this same rigor to the final execution path, the polar-to-worker pipeline under adverse system conditions. We start by simulating an operating system interruption to test our graceful shutdown sequence. This animation illustrates the shutdown test. We start the worker, then send a SIG-term signal. The system must block new incoming webhook requests. We verify all in-flight deliveries are allowed to complete their journey before the process terminates. Finally, we test the ultimate failure boundary, the dead letter path. We configure the system with a retry limit of 2 and force the mock receiver to fail continuously. This diagram shows the final state transition. After exhausting its final retry attempt, the system pulls the event out of the active queue and moves it into a dead-lettered state. Moving failed events to a dead-letter queue is critical to prevent infinite polling, which would eventually saturate the worker pool and stall the system. Testing these edge cases at the operating system and worker level ensures the service degrades predictably rather than crashing under heavy load. This completed architectural diagram shows how our specific tools map to each system layer. At the center, we use pure Go tests to validate isolated domain math. We use test containers in the middle layer to verify transactional SQL locks. And we apply HTTP mock servers to the outer boundary to validate the end-to-end lifecycle and signal handling. This layered perimeter validates our delivery logic at every stage, providing the high level of confidence needed to handle network anomalies and concurrent scale. With our code logic verified, our next step is to make this execution visible at runtime. Establishing this verified testing perimeter forms the foundation we need before implementing structured logging and distributed tracing. We'll build that observability next episode.